Okay, 6.5b, more operations of a complex number. Just a quick reminder from last time, the way we multiply and divide our trig form of complex numbers. If you care, by the way, r is called the modulus and theta is called the argument. I'm not going to test you on that. I don't use those terms when I talk about it either. But if we were doing these two problems and I wanted to do z1 times z2, remember you multiply the modulus, the r's together, and then you, for multiply, you end up adding the arguments, the thetas, together. Multiplied is 36. Common denominator times 2 on top and bottom. 4 plus 17 is 21 pi over 6 for multiply. For divide, you divide the modulus and you subtract the argument, you subtract the thetas. So that's going to stay 9 over 4 times 2, so 4 minus 17 is going to give me negative 13 pi over 6. Too many overs, over 6. And that was how we multiply and divide. So that brings us to Moivre's theorem. If you keep doing that, if you keep multiplying z1 times z1 times z1 times z1, what do we use to show multiplication over and over again? We use exponents. So you can see in his theorem here, if you work it all the way through, if you keep multiplying it over and over and over again, z to the power of n is going to be r to the power of n, because the rule for exponents is that you multiply them each time. So if I multiply it 5 times, that's the same thing as r to the 5th. But then for your CIS, the rule for the thetas was that you add them over and over and over again. So if I do theta plus theta plus theta plus theta 5 times, I'm going to get theta times 5, or theta n. So this is kind of a shortcut to help us do complex numbers raised to a power. But it only works if you're in trig form. So our first step is going to be to change it to trig form. Okay, so the reason we want to go to trig form is because trig form has a nice formula, right? The one I just wrote down. If you were to leave this in complex form, you would have to do 4 minus I root 3 times 4 minus I root 3, which is an area diagram for you guys. Once you get that answer, you'd have to do that answer times 4 minus I root 3. 4I root 3. You get what I'm saying. And you'd have to do it until you had multiplied 9 of them together. So that's why the formula is handy. So in order to do that, we need to sketch it and go from complex form to trig form. So practice that from last class. Positive 4, negative 4 root 3. Connected to 0, 0. This was positive 4. This was negative 4 root 3. We need r and we need theta. R squared is going to be 4 squared plus 4 root 3 squared. See if you could finish the math. See if you can find theta. In this quadrant, there's 1, 3, so it's something pi over 3, but it's all the way around in the 4th quadrant, so that must be 5 pi over 3. So the original problem, the complex form, could be written as 8 CIS, 5 pi over 3. But remember, they're trying to do that to the 9th. So now I'm going to use my new formula. Formula says you can take r and raise it to the 9th because you're going to multiply that 9 times. But for theta, you're going to end up adding it 9 times. So 5 pi over 3 times 9. 8 to the 9th, if you had a calculator, is this. CIS, and then 9 divided by 3, this is 15 pi. I don't know why I put it up in the air. It's just 15 pi. And we did it in, well, we switched it, and then after that we did the power in one nice step versus doing 8 area diagrams. Okay, let's try another one. So sketch it, find r and theta. Maybe pause the video and see if you can find r and theta on your own. Negative 3, positive 3. quadrant 2, where tangent is -1, that is 3 pi over 4. So the original problem could be written as 18 CIS 3 pi over 4, but they want to raise that to the 10th power. So 8 to the 10th, CIS 3 pi over 4 times 10. If you have, wait, where did I come up with 8? Sorry, let's go back. R is root 18, so let's fix it here. Root 18, so this is root 18 to the 10th. Okay, write it down correctly. If you don't have a calculator, you could leave it as root 18 to the 10th. I believe root 18 to the 10th is this. CIS, and then times 10, divide by 2, 15 pi over 2. And one nice step. Okay, so then we can also use that same theorem idea to find the roots of a complex number. So I know the equation looks kind of crazy. Let's just jump into number 4. So even though there's no plus 0i, we still want to think of it as a complex number, and we still want to graph it. So -8 on the real, 0 on the complex would put it here. We don't need to make a triangle because we could just see that r is 8 because r is a distance. And theta, if we're over there on the unit circle, theta is going to be pi. So when it says find the cube root, they're basically telling you to do this. And I understand that we could do this one just on our own without the theorem. But if we want to use it, we want to do cube root of 8 CIS pi. Okay, so let's match everything up to our formula. So, r is 8, theta is pi. In our problem, we're doing cube root, so n is 3 for this problem because they asked us to find the cube roots. And then k is all the way up to n minus 1. So since n is 3, k is going to be all the numbers, 0, 1, 2. It has to be one less than your exponent, n. Okay, so let's plug this into the formula. So we're doing the cube root, because that's what the question wanted. And for us, so that was n, r is 8. And then it is times cosine. For us, theta is pi plus 2 pi n, 2 pi k, sorry, over n is still 3 for us, plus I sine, that's kind of a big gap, I sine pi plus 2 pi k, still over 3. Okay, so this is what we're going to be doing. Cube root of 8 is cube rootable, so I'll simplify that one step. So what we're going to do is we're going to go through for all of our k's, k equals 0, k equals 1, k equals 2, I don't know how much space it'll take me, and we're going to plug those in for k in each of these. So 2 pi times 0, I'm plugging in 0, is just going to be 0, so this will just be pi over 3 plus, and it's going to be the same for both of them. Pi over 3, with or without the parentheses is fine. Well, each of those can be done, right? So at pi over 3, I don't know where I'm going to draw my unit circle over here. Pi over 3 is there. What's cosine at that spot? It's 1/2 plus I. What's sine at that same spot? It's root 3 over 2. So then if you multiply by that 2 out front, distribute your 2, you get 1 plus I root 3. And if you took the time and you cubed that, so you did that times itself in an area diagram and then one more time, you end up getting -8, which is not a number we would have thought of when we think of the cube root of -8, right? So this is part of the fundamental theorem that says that for every positive integer n, there are always n distinct roots, which is why we're going to get 3 answers when we finish this, because we're going to plug in 0, that's one answer, 1 is another answer, 2 is another answer. So let's go ahead and plug in 1. I'm going to change colors actually. To the same formula. So I simplified our formula down to this. That's where we're plugging things in. We are plugging in k equals 1 now. Two pi times 1. I'm going to go vertically this time. So this is cosine of 3 pi over 3, right? 3 pi over 3, which is just pi, plus it's going to be the same. This is doable on the unit circle. At pi, here's my tiny picture of pi. It's over there, right? Cosine is -1, plus I sine over there is 0, which gives us -2, which is the answer we would have come up with on our own. But remember, there's always complex roots as well. So our third solution, plug in 2. 2 pi times 2 is going to be 4 pi. Oops. Pi over 3 is where we're at. Tiny picture for 5 pi over 3, almost 6. At that spot, actually I'm going to go down here. Cosine at that spot is 1/2. Sine at that spot is -√3 over 2. Distribute the 2 and you get 1 minus I√3 or √3i, however you want to do it. That's our third root. If you did that times itself again, you would get that -8 answer. Okay, let's try one more. 16i, remember it's 0 plus 16i. So 0 for the real, 16i for the imaginary, so it's approximately there. R is going to be 16 because it's the distance from 0. And then theta on the unit circle, once you're up there, theta is pi over 2. This says fourth roots, so n is going to be 4. So that means our k is going to go 0, 1, 2, 3. Okay, let's plug it into our formula. We are doing the fourth roots of 16i. Instead of writing the 16i there, I want to write z. Fourth root of z. Z was this, but then we just changed it. R is 16, CIS, pi over 2. So we are going to plug it into our formula. So it's going to be the fourth root of our R is 16, times cosine. Our theta is pi over 2, plus 2 pi k, all over. Our n is 4, plus I sine the same thing. So if we work on simplifying our formula down, 4 through the 16, what to the fourth makes 16? It's 2. If we multiply our fractions all by 2, everybody by 2 to get rid of the fractions inside the fractions, these 2's will cross out. Don't forget the cosine. This will be pi plus 2 times 2 is going to give me 4 pi k over 4 times 2 is going to give me 8, which will just make it a little easier as we're doing the problem. Same thing's going to happen over here. And this is what we're going to plug things into. So let's start with k equals 0. So 2 cosine. We're plugging in 0 for k. 4 pi times 0 is going to be 0, so pi over 8 plus I sine is going to be the same thing, pi over 8. Pi over 8 is not on the unit circle, so we can just simplify this down to 2 CIS pi over 8, and that would be one of our answers. If it doesn't work out on the unit circle, we're just going to stop there. K equals 1, 2 cosine pi plus 4 pi, right? 4 times 1 is going to be 4, so 5 pi over 8 plus I sine 5 pi over 8 means 2 CIS 5 pi over 8 would also be one of our roots. K equals 2, 2 cosine. 4 times 2 is going to be 8 plus pi is going to be 7 pi over 8 plus I sine 7 pi over 8, which is 2 CIS 7 pi over 8. And our last one, k equals 3. You end up with 4 answers because we were doing fourth roots. 2 cosine. We're doing 3. 3 times 4 is 12 plus 1 more is 13 pi over 8 plus I sine 13 pi over 8, which is 2 CIS 13 pi over 8. Maybe we should go back and fix my math, because 4 times 2 is 8 plus 1. The green ones should have been 9. Hopefully you caught on if you were doing that one on your own. Make those 9. And these are our fourth roots of 16i. That is it for today, and I hope you guys are doing good.